Hello everyone, welcome to my presentation. My name is Edmond.irani. I am from the Cyber Physical Systems Group of Technical University of Munich, led by Professor Matthias Althoff. In this work, we propose a method to compute specification-compliant reachable sets for motion planning of automated vehicles. Highly automated vehicles, or AVs for short, promise increased road safety compared with human-driven ones. To safely and effectively participate in road traffic, AVs should explicitly consider compliance with traffic and handcrafted rules. Compliance with the former exempts manufacturers from potential liability claims in case an accident happens, whereas the latter contribute to finding motion plans that meet specific requirements. An example of which can be follow vehicle A up to time step K1, then finish overtaking it from the left before time step K2. Determining a drivable trajectory that satisfies a desired discrete specification is challenging. This is because we need to consider vehicle dynamics and collision avoidance, discrete specifications, and interdependency between continuous trajectories and discrete constraints posed by the specification. In this study, we extend our previous work and propose a method to compute specification-compliant reachable sets for a considered ego vehicle, which expedites the search for a trajectory meeting the mentioned characteristics. Notably, our reachable sets are over-approximative and enclose all drivable trajectories. With that in mind, an empty reachable set that implies no feasible trajectory can be planned that satisfies the considered specification. On the other hand, a non-empty reachable set can be used as trajectory planning constraints on position, velocity, and time. We now proceed with the preliminaries of the work. All experiments are carried out with scenarios described in the CommonRoad format. The major elements are lanelet network, obstacles, and planning problems. The yellow region in the figure represents the goal region of a planning problem. We construct a local curvilinear coordinate system from the reference path leading from the initial state to the goal region. Prediction of other vehicles over time are based on the trajectories provided in the scenario. To compute the reachable sets at the later step, the system dynamics of an ego vehicle is first abstracted by a point mass model with the center of the vehicles as the reference point. The model is represented with two second-order integrators in longitudinal direction and lateral direction of the curvilinear coordinate system. We attach subscripts S and D to variables to indicate these directions, respectively. The given system is 5-dimensional, containing positions, velocities, and time. And the input to the system is acceleration in the longitudinal and lateral directions. Next, we introduce the notion of reachable sets. The reachable set of a system is defined as the set of all states that can be reached at a given time step k, starting from an initial set of states. As mentioned earlier, we over-approximate the reachable sets and represent them with the unions of so-called base sets, each of which is a Cartesian product of two convex polytopes. In the bottom figure, we show these polytopes and their projection onto the position domain. Each base set is represented by a node in the so-called reachability graph, which is directed with edges indicating their reachability over time. Each node carries a set of semantic labels L, which are predicates that evaluate to true for the node. This table lists the selection of predicates that we consider in our work, which are sourced or inspired by our earlier formulation of German road traffic regulations using metric temporal logic. The predicates are grouped and categorized. Evaluating a dynamic predicate is obstacle dependent, whereas that of a static predicate is not. Now we concisely explain the two major steps of our method. The first step being semantically labeling reachable sets with relevant predicates, which in turn has two substeps, which are formulating partitions of state space with respect to position predicates and computing reachable sets with semantic labels. The second major step is checking compliance against time-labeled propositional logic. We proceed with explaining formulations of partitions. Partitions of state space are modeled as sets of hyperrectangles. These hyperrectangles are again Cartesian products over the position and velocity domains. Notably, such a choice is not mandatory. Any other representation that captures the partition suffices. Let P denote a set of considered position predicates, and Z subscript J a combination of position predicates, which is also an element of the power set of P. We define an operator part that accepts time step and a set of position predicates to represent a partition, which is a collection of hyperrectangles for which predicates in Z evaluate to true. In the figure, we show the projection of the partitions onto position domain at different time steps. Each color represents a set of position predicates with respect to the lanelets and other vehicles. We now explain the computation of reachable sets. Most of the steps are similar to the ones described in the reference paper. In addition to our previous work, the base sets are split with respect to position and velocity predicates such that they can be unambiguously labeled. The figures illustrate the propagation and splitting of an exemplary base set in the longitudinal direction. In subfigure A, the polytope is propagated from the one of the last time step. In subfigure B, the polytope is split to unambiguously intersect with one of the formalized partitions. In subfigure C, the polytope is split into three new polytopes with respect to two velocity predicates v1 and v2. In reality, these predicates may be introduced by minimum and maximum split limits. In the last figure, the polytope is split by the safe distance profile with respect to a leading vehicle. Notably, due to the non-linearity of the curve, we slightly over-approximate the split results to restore the convexity of the polytopes. After splitting the base sets, predicates relating to acceleration and general traffic situations that evaluate to true are also attached. All predicates that evaluate to true are stored in the set of semantic labels L introduced earlier in the reachability graph. The considered specification are expressed in time-labeled propositional logic, which has the illustrated form. The last operator indicates that the expression should always hold for the interval indicated by letter I. If I is unspecified, we assume it to be the entire planning horizon. We show few examples of specifications along with their interpretations. The first demands that for time steps in between 0 and 15, ego vehicle should be in lanelet 1. The second demands that for all time steps, the ego vehicle is behind and aligned with vehicle 1. The third demands that for all time steps, ego vehicle respects safe following velocity to all vehicles, does not drive on the right of vehicle 2, and does not change from lanelet 3 to lanelet 4. We now evaluate our method on three scenarios. The animations of resulting reachable sets over time are displayed alongside their specifications. The specifications on the bottom may be issued by a high-level maneuver planner, which should be precisely followed by the ego vehicle. The resulting reachable sets are non-empty, thereby implying that one may find a trajectory that satisfies the specification. We show the reachable sets over time, as well as an exemplary trajectory planned within the reachable sets. In this scenario, the ego vehicle is driving on the left side of two other vehicles v1 and v2, and wishes to change to lanelets on the right. The unrestricted reachable sets show that the ego vehicle can deliberately cut in between v1 and v2. By contrast, after considering the specification with safe velocity rules, being in between v1 and v2 is no longer legal. Finally, we present a scenario in which the ego vehicle intends to overtake its preceding vehicle v1. In the case of considering specification, the reachable set overtakes v1 while not being on its right and not entering lanelet 4 for the entire duration. To conclude, we have proposed a method for computing specification-compliant reachable sets which integrates predicates considering position, velocity, acceleration, and general traffic situations, and can consider traffic and handcrafted rules. We have also shown with an example that this can be used as planning constraints for trajectory planning. As of future work and possible extensions, We plan to investigate the compliance with the specification expressed in metric temporal logic, which supports temporal operators with precise time intervals. We will also adapt the method to apply to more traffic rules. In addition, incorporating set-based prediction into the computation is also worth investigating. Thank you very much for your attention.